Yeah, so today's lecture is going to be about some strong correlation phenomena that can occur in topological semimetals that they have not been observed yet, but this is something that can happen in principle. So this is the outline. So in the first part of the talk, I will talk about this three-dimensional generalization of fractional quantum Hall effect that, again, can in principle occur in magnetic wire semimetals. And the second part will be about localization in topological semimetals. So this is not strictly a strong correlation phenomenon. No interactions are required here, but because the theoretical description of localization has a lot of parallels to strong correlation phenomena, in particular to low-dimensional magnetism, I've included this into this lecture. But I don't know how much time I will have to go through this. Okay, so yesterday we talked about the topological response of these semimetals, which is basically described by these topological terms with fractional coefficients, right? And so a natural question we can ask is, can we get a gap symmetric insulator that has the same response? Okay. Well, so certainly whenever you have something gapless, it's a good question to ask, can I open a gap? And what happens, right? The motivation for this question besides that is that so this kind of an insulator that has exactly the same response but just gapped, this would be an insulator that's in some sense closest to a given topological semimetal, right? I'm not changing anything except opening a gap. So that's the question I want to ask. Now, as we discussed, a generalization of Lipschutz-Matisse theorem says that an ordinary insulator like that is impossible. So basically, we must have either broken symmetry or topological order. So, and I don't want to have broken symmetry because this is too simple. Okay. So basically, if such a symmetric insulator with the same topological response as a topological semimetal exists, it must have topological order. And the question is, what kind of topological order that is? Okay. And so in particular, I will focus on the simplest but also the most interesting case, the case of magnetic wire semimetal. And so if we do manage to construct such an insulator, it will be basically a three-dimensional generalization of the fractional quantum Hall effect, because as we discussed, a magnetic wire semimetal is characterized by a Hall conductivity that's fractional per atomic plane. Okay? So if I can open a gap without breaking any symmetries, I get three-dimensional fractional quantum Hall effect. Okay? And as I will explain, this is actually possible, quite surprisingly. So you may think that 3D generalization of fractional quantum Hall effect is not possible for several reasons that I will discuss. Okay, so again, so this is what we want to do. So we have, let's suppose we have a magnetic wire semimetal, the simplest one with just a pair of nodes separated by some wave vector in the brilliant zone. So as we discussed last time, this is its topological response, which just expresses the fact that I have a Hall conductivity of lambda times E squared over H, or lambda over 2 pi in the units where E is equal to H bar is equal to 1, which I will use here. Okay, and so the question is, can I gap the wire nodes while preserving this response? Okay, and let me first tell you why this is really difficult. Okay, so well, we talked about the Lipschutz-Matisse theorem, but there is a simpler kind of pictorial way to understand why this is difficult. So something that I did not discuss in my lecture, but this was covered in Su Yang's lecture, actually, is that this Hall conductivity actually comes entirely from the surface states of this semimetal, which have the form of Fermi arcs. This is a chiral state that connects the projections of the wire points on the surface brilliant zone. Okay. So this red line here represents the Fermi arc, and its dispersion is chiral in the direction into the screen. Now, So then the question becomes, what do I do with this state if I open a gap, right? Fermi arc cannot simply stop at an arbitrary point in the brilliant zone like that, right? Now, one thing I can do is I can break translational symmetry, right? I can create a charge density wave at this wave vector connecting the nodes, and this is actually the simplest way to open a gap. In this case, there is no problem because then the brilliant zone is shrunk, right? And the former locations of the while nodes become just the boundaries of the brilliant zone. Okay, and then I can open a gap, and the Fermi arc then it's not an arc, it just spans the whole brilliant zone. Okay, so then that's not a problem. But as I said, I don't want to do that. I don't want to open a gap in a trivial way where I just resize the brilliant zone. I want to open a gap while keeping the symmetry of the translational symmetry of my while semimetal. I want to keep the same size of the brilliant zone. So then it seems like this is impossible because what do I do with the Fermi arc? Now, so if you think about this for a while, then you come to the conclusion that the only thing you can do to circumvent this problem is the following. What you can do is split the Fermi arc into a Majorana state, right? And since Majorana is half a fermion, okay, it's the length of the Majorana state is in the surface brilliant zone is going to be twice the length of the Fermi arc. And so then, for a particular separation between the while points, when the distance to Q is equal to exactly half a reciprocal lattice vector, then everything works out. My Majorana state, my chiral Majorana state, is going to span the whole brilliant zone, and I can open a gap without resizing the brilliant zone, without breaking translational symmetry. Okay? Now, so this chiral Majorana surface sheet, this is exactly like the surface state of a stack of topological P plus IP two-dimensional superconductors, right? So you know that a P plus IP topological superconductor has a one-dimensional chiral Majorana surface edge state. So if I make a stack of them, then this is going to give me a chiral sheet of Majorana states that's going to cover the whole brilliant zone. Okay. And so this gives me a hint of how to actually construct, in theory, such an insulator. Okay. So what I want to do is start from a three-dimensional P plus IP topological superconductor, which is a stack again of two-dimensional P plus IP superconductors, and then disorder the superconductivity by condensing vortices in this superconductor while keeping the pairing gap. Okay, so this is not this kind of superconductor to insulator transition is not unprecedented. This happens in real systems, like for example in amorphous films in 2 dimensions, and so this is in principle possible. But this is of course not. You should not view this as a prescription for an experimentalist of how to obtain that state. This is just a theoretical procedure of how to construct such a state. Okay, so again, I'm going to start from a three-dimensional P plus IP superconductor and condense vortices in that in an attempt to construct a state, an insulating state that has the same response as a while semimetal, where the separation between the while nodes is exactly half a reciprocal lattice vector. Okay. Now, let me actually first talk about a very similar problem in 2 dimensions, okay, in the more familiar context of 2-dimensional fractional quantum Hall effect, because it's going to be simpler to explain what I'm going to do. Okay. Now, the connection to 2D quantum Hall effect here is very simple. So if my separation between the nodes is half a reciprocal lattice vector, so this means that this parameter lambda here is equal to a half. So in other words, I have half Hall conductance quantum, half E squared over H per atomic plane. Okay, and so in 2 dimensions, this is realized at the integer quantum Hall plateau transition, right, between E squared over H and 0. which, as you know, probably can be described in terms of a gapless, massless, two-dimensional Dirac fermion. Okay, so this is a description of the of the 2D quantum Hall plateau transition in terms of the Dirac fermion. Right? Let's say I have sigma xy equals 0 when the gap is positive, and then I take it through the transition, or where I change the sign of the gap. Right, this goes to sigma xy equals e squared over h, and so right at the transition, I have sigma xy equals e squared over 2h, and this corresponds to this massless Dirac fermion. Okay, so again, Su Yang talked about this in the previous lecture. This was first realized by Holming. And so the question that's exactly analogous to what I want to ask in 3 dimensions for the YL semimetal here is the following. Can I take this massless 2D Dirac fermion and open a gap while keeping the Hall conductivity to be e squared over 2h? Okay, so this is clearly impossible without creating some kind of fractionalized state with topological order, because ordinary 2-dimensional insulator must have an integer Hall conductivity. Okay, again, for the same reasons, this is another incarnation of the Lipschutz-Matisse theorem. Okay. And so we may construct this state by the same procedure that I'm going to apply in 3-dimensional case. I want to start from a gapped superconductor and disorder its phase, meaning condensed vortices, while keeping the pairing gap. Okay. Okay. So let me walk you through this procedure. So if I add the simplest S-wave pairing to a massless Dirac fermion, what I get actually is a fully gapped topological P plus IP superconductor. So this has been discussed extensively in the context of superconductivity on the surface of 3-dimensional time reversal invariant topological insulator that has precisely massless Dirac surface states. So this has chiral Majorana surface state, and a consequence of that is that if I induce a vortex carrying the superconducting flux quantum, so hc over 2e, right, or pi in my units where h bar is equal to e is equal to 1. So if I induce a pi flux vortex, this is going to carry a Majorana zero energy mode in its core. Okay, so you know that in 2 dimensions, vortices are particles. So in principle, you can think about them as bosons. Okay, and so there is a superconductor to insulator duality or charge flux duality, which says that I can describe an insulator as a Bose condensate of vortices. Okay, so if I take a superconductor in 2 dimensions and condense vortices, which move like particles, then I get an insulator. Okay, without breaking the pairing gap. But so in this case, this is impossible because these vortices here are not bosons, since they carry this Majorana zero energy mode. Okay, so they are actually non-abelian anyons for this reason, and they cannot be condensed like bosons. Okay, so I cannot condense this vortex to create an insulator. Now, well, what we can do is ask, can I condense double vortices, namely flux 2 pi or hc over e vortices? Okay, so those vortices will have a pair of Majoranas. Okay, and a pair of Majoranas can always be converted into a real fermion, and those are generically gapped just by the pairing interaction itself that creates the superconductor. Okay, so those vortices don't carry any gapless modes in the course, and so naively we may think that such vortices can be condensed. Okay, now, but it turns out not to be the case, and so this has to do with the fact that I have to remember that I want to preserve my Hall conductivity of e squared over 2h, right? And it follows from this topological term that describes that Hall conductivity, that actually a vortex with this flux carries a charge of E over 2, right? So that's, well, that's another kind of well-known property of quantum Hall systems, right? That magnetic flux draws in charge. That's proportional to the Hall conductivity. So in this case, the flux of 2 pi is going to bring in charge of E over 2, right? Because the Hall conductivity is E squared over 2h. And in addition, such fractional charges are going to be semions. They're going to have semion exchange statistics. The statistical angle is also proportional to the Hall conductivity, so they will have the statistical angle of pi over 2, so they're semions. Okay, so again, these are not bosons and cannot be condensed. So the smallest vortex that is a boson and can be condensed is actually quadruple of the elementary superconducting vortex. So it's flux 4 pi or 2hc over E. Okay? And now the condensation of such composite vortices actually immediately implies fractionalization at topological order. So this is because basically the charge of the elementary excitation times the elementary flux quantum, the product is always equal to 2 pi, right? So this is the dual of, you know that when you form a superconductor, when the electrons pair up, the flux quantum gets halved, right? For non-interacting electrons, for unpaired electrons, the flux quantum is hc over E. But in a superconductor, the flux quantum becomes halved. It's hc over 2E. So the dual of that is that if I condense vortex composites, I get charge fractionalization. Now, so mathematically, this kind of state can be described by basically a standard composite fermion construction. So I can write my electron as a product of this neutral fermion, F, which is basically the composite fermion, and a boson, and I will call it H, that carries charge. Okay? I mean, it would be more logical to call it B, but B is reserved for something else here, so I'm going to call it H. And so what I do to construct this state, I place my composite fermions or spinons into the 2D P plus IP gapped superconductor, while condensing these flux 4 pi vortices in this boson that carries a charge. And so the theory that describes this looks like this. So I can write, so this is the standard construction in the field theory of 2D fractional quantum Hall effect. I can write my charge current that's carried entirely by this boson as a curl of a gauge field, B. Okay. Now, in addition to conservation of charge, vorticity is also conserved here. So similarly, I can write the vortex current as a curl of another gauge field, C. Okay. And in this language, the composite fermion, the standard composite fermion construction would be to place my bosons into a nu equals a half Laughlin state. Okay. Now, if I do that, I will actually get wrong response, not the same response as a Weil semimetal. So the way to get the right response here is to go to a more complicated hierarchy state, where I actually place the vortices into the nu equals a half Laughlin state. And so this is described by this theory, which can be expressed by this kind of K matrix, a 2x2 K matrix. Okay. So, well, I mean, I can see that this corresponds to the right response very easily. So if I integrate over this gauge field B here, what this does is basically it sets this gauge field C, which expresses the conserved vortex current, to be equal to small a, which is just a statistical gauge field, which glues together the composite fermion and the boson. But this one is actually gapped by the Higgs mechanism, because the composite fermions are in a paired P plus IP superconducting state. So I can forget about small a. So then C is just equal to minus a over 2, where a is my external electromagnetic probe field. Okay. And so if I plug this back in here, I get precisely the right Hall conductivity of my wire semi-metal, which is E squared over H per atomic plane, just E squared over H. Sorry, I'm still talking about 2 dimensions. And then the second term tells me that the excitations here, the charged excitations, are bosons with charge 1/2. Okay, so this coefficient here is the charge of my quasi-particle excitations. Okay, and so basically what this is an example of a non-abelian even denominator quantum Hall state. So in the context of so this was discussed recently in the context of similar problem for gapping the surface states of topological insulators without breaking any symmetries. And so this state was called 5-fan anti-semyon there. Okay, so it's one of several possible non-abelian even denominator fractional quantum Hall states. Now, so this is the electrical response, and that comes from this from condensing vortices in this boson field. Now, the thermal response comes entirely from this P plus IP superconductor of composite fermions. They're neutral, so they don't contribute to the electrical response. Okay, but they give exactly the same thermal response as a non-interacting wire semimetals. Wire semimetal basically by construction, because the H state is a chiral Majorana state that precisely gives me a half quantum of the thermal conductance. While the bosons actually don't give me any contribution to the thermal conductance, because the H state structure, so remember that this state has this 2x2 K matrix. What this means is that there are actually 2 edge modes that correspond to that, and those edge modes are counter-propagating. So one of those edge modes is charged, and that gives me this Hall conductivity, while the other one is neutral and counter-propagating. So the thermal Hall conductance that's coming from bosons is 0, and it's coming entirely again from this from the Majorana H state that comes from paired composite fermions.
Is it quantized to 1/2, or what's the value?
Yeah, it's quantized to 1/2. So it's the response again is exactly the same as a non-interacting gapless Dirac fermion, right? So there is a half quantized electrical conductivity, and by Wiedemann-Franz law, the same half quantized thermal conductivity. Okay, so now let's move on to the 3-dimensional case, and basically what I'm going to do is construct an exactly analogous state in 3 dimensions now. Okay, but this will still be a non-trivial generalization. It's not simply a stack of those 2-dimensional states in 3D. Okay, but the procedure is very similar. Okay, so the first thing we need to do is figure out how to gap the while nodes by pairing. Okay, and even that actually turns out to be non-trivial. So there are 2 superconducting states that you can imagine here. The first one is the simplest BCS state, where I pair time-reversed states, so spin up here and spin down here, okay, K and minus K. So this is internodal pairing, because I pair states in the vicinity of different nodes. Now, another possible state is where I can pair spin up and spin down states on the 2 sides of the same while node. Okay. Now, this state, will actually the Cooper pairs will carry a non-zero momentum, which is going to be just equal to twice the momentum of the node, and so this state I can call FFLO, right? Because it has a non-zero. The Cooper pairs have non-zero momentum. Now, it turns out that BCS state is actually not, BCS pairing is actually not good for our purposes because it doesn't open a gap. So you do get a superconductor, but the superconductor is gapless, basically because, pairing does not actually mix the two chiralities. Okay. Now, the FFLO state does open a gap, but here we get another problem that, again, because Cooper pairs carry momentum, this state actually breaks generally translational symmetry, which I explicitly don't want to do. I want to create, again, a symmetric state with the same response. so a state that has the same symmetry as the wild semimetal and the same response. But it turns out that, again, exactly for this separation of wild nodes, where 2q, the distance between the nodes, is equal to a reciprocal lattice vector, there is actually a way out. And the way out, and this is because the density modulation that corresponds to this kind of pairing actually carries momentum 4q. So it's twice the momentum of the Cooper pair. Okay? And when q is equal to g over 4, or 2q is equal to g over 2, 4q is equal to g. So it's equal to a reciprocal lattice vector. And so miraculously, actually, the FFLO state, in this case, does not break translational symmetry. It has exactly the same symmetry as my original wild semimetal. Okay? So everything works out in our favor, right? We can gap out the nodes because we can split the Fermi arc into Majorana, right? And also the FFLO state does not break translational symmetry. Well, it's of course not an accident, but it's interesting how everything works out to help us in this case. Okay? And so then I can construct the exact analog, basically, of this two-dimensional non-abelian fractional quantum Hall state that I talked about before by following the same procedure, just generalized to 3 dimensions. So again, I can write my fermion as a product of a neutral composite fermion and a charged boson. Okay? I place my spinons now in a 3-dimensional P plus IP superconductor, which is that FFLO state. Okay? It's the FFLO state is also can also be thought of as a stack of 2D P plus IP superconductors, which carry Majorana modes. Okay? Now, so there are some differences from 2D. So in particular, again, I can write my conserved charge current as a curl of some gauge field, but because now I have an extra index, that gauge field will have to be a 2-form gauge field. So it's B alpha beta. It carries 2 indices. Okay. Now, physically, what this expresses is the fact that, so in 2D, as I said, you can think of vortices as particles, right? And those vortices actually are minimally coupled to this gauge field. Now, in 3 dimensions, of course, vortices are no longer particles. They are lines or strings, okay? And it's those strings that couple to this 2-form gauge field now. These are strings that are minimally coupled to this 2-form gauge field. Okay? Now, so similarly, the vortex current, so the vortex current, again, since vortices are strings, and the vortex current now carries 2 indices, J mu nu, and I can write that as a curl of now a 1-form gauge field. And so quasi-particle excitations, which are bosons in this case, are coupled to this 1-form gauge field. Okay? And another difference is that I have to, in this topological term, which looks very, for C, which looks very similar to what I had for my point-like particle vortices in the 2D case. So now I need to include a translation gauge field in here. And this just expresses the fact that if I want to have 3-dimensional quantum Hall effect, I need to specify a family of planes in which the Hall conductivity is going to be non-zero, right? It cannot be non-zero in all possible families of planes, right? So in this sense, this 3D quantum Hall effect is different from 2D. In 2D, everything is symmetric in a quantum Hall liquid. Here, there is a preferred direction. Okay, the translational symmetry is preserved, but there must be a preferred direction, which tells me in which planes the Hall conductivity is non-zero. Yeah.
So how do we interpret a 2-form current?
Oops, sorry. How do we interpret?
The J mu, it's a 2-form, right? So
yeah. So well, this is the so in case of a particle, I guess. So particles propagating in time. There are the word lines of particles. So these currents can be viewed as describing those word lines. Now, a 3-dimensional vortex is a string, So this sweeps out a world sheet, a two-dimensional surface, and so this is described by that two-form current. Okay. And so again, I can easily show that this kind of state gives me the right response, right? So if I integrate B, I get C equals minus A over 2, and so again, I get the right response. So this is exactly the whole conductivity of a wire semimetal with conductivity 1 over 4 pi, or E squared over 2H per atomic plane, right? And the second term again tells me that that the quasi-particles are charged bosons with charge 1/2. Okay? While again the thermal response is entirely contained in this three-dimensional P plus IP stacked superconductor of my neutral composite fermions. Okay. Now, so let me point out one very important thing. So another reason that you may doubt that the three-dimensional fractional quantum Hall effect is possible is anyons, right? So you know that in the usual two-dimensional fractional quantum Hall effect story, the existence of anyons or particles with fractional statistics is very, very important, right? But anyons can only exist in 2 dimensions, which makes you doubt that a 3D generalization of fractional quantum Hall effect is even possible, even in principle. So how is this avoided in our construction? Well, so in our case, of course, quasi-particle excitations are only bosons or fermions. There are no anyon quasi-particle excitations. Now, in the 2D fractional quantum Hall story, the anyons arise as vortices actually. Okay? So it's the vortices that are anyon excitations. In our case, vortices are lines. They are not particles, they are strings. Okay? But anyons actually are hidden. They emerge as intersections of these lines with XY atomic planes. Okay? So basically, if a flux pi, or Hc over 2e, line penetrates any XY atomic plane, at the intersection point, it induces a Majorana and a charge 1/4. Okay? If I take flux 2 pi, a double vortex, then this is going to induce a charge 1/2 semyon. Okay? And so that's the analog of the 2D fractional quantum Hall physics in here. Okay? So the anyons are still there, but they cannot propagate this as independent quasi-particle excitations. They're just intersection points of these vortex lines, vortex strings with atomic planes, right? So this is similar in principle how, in string theory, people talk about, particles induced by intersections of strings with branes, right? So this is a similar idea here. And well, so experimentally, what is going to be the manifestation of that state? Well, so as we discussed in the previous lecture, I can think of my magnetic wire semimetal as an intermediate phase between an ordinary insulator and an integer quantum Hall insulator with Hall conductance of E squared over H per atomic plane, and in between this Hall conductivity changes smoothly as a function of, let's say, magnetization. Right? So this is like a broadened two-dimensional plateau transition. Okay? But so if this three-dimensional fractional quantum Hall state is realized, basically what you're going to see is that this smooth evolution of sigma xy, this magnetization, is going to be interrupted by a plateau that corresponds to Hall conductivity of exactly half of this integer value. So E squared over 2H per atomic plane. Okay? And so if I don't break any symmetries, if I don't break the translational symmetry in the process of opening this gap, then this state is going to be this three-dimensional fractional quantum Hall state. Okay? Okay, any questions for the first part? Well, right. So because this this state is gapped, right, and there is this plateau, you don't need to tune exactly to the separation of g over 2, right? As long as you are close, this is going to be tolerant to small deviation because this state is gapped.
Okay. It's best described with this q over 2 state.
Right. So I can construct it by starting from a non-interacting wire semimetal at exactly that separation, but in principle it does not require that. Okay, so well, if there are no more questions, let me move on to the second half of this talk. And so this is not going to, again, involve any interactions. This is going to be about localization, but well, I still included it into this talk. Well, at least because I just didn't have time in the previous lecture. Okay, so here is the question that I want to ask. So we know that any three-dimensional metal becomes an Anderson insulator, which is compressible like a metal, but has a zero conductivity at zero temperature, right? Becomes an Anderson insulator with sufficient amount of disorder, right? And since, well, we are saying that topological semimetals is another way a metallic phase may be realized, it's a natural question to ask, is the same true for three-dimensional topological insulators? So will they become Anderson insulators with sufficient amount of disorder? Okay. So actually, just as for in the first half of this talk, there is going to be some analogy here to the two-dimensional quantum Hall plateau transition. Okay. So we know that in 2 dimensions, all states are always localized except at the quantum Hall plateau transition, right? So this is this famous picture of plateau transitions and corresponding peaks in the diagonal resistivity at the plateau transitions, right? So everything is localized in the plateaus, but right at the plateau transitions, you have delocalization. As I already mentioned several times, we may think of so let's again talk about the simplest case of magnetic wire semimetal, even though this story is generalizes to other semimetals, but let me talk about the simplest case. So I can think of my magnetic wire semimetal is basically like a broadened plateau transition, right? So the plateau transition in 2 dimensions has to be sharp because the Hall conductivity is just quantized in integer units of e squared over h, right? And it's impossible to go smoothly between 2 integers. So in 2 dimensions, the plateau transition has to be sharp. You have to jump from one value to another. Now in 3 dimensions, since the Hall conductivity involves a wave vector, there is no reason that a wave vector has to jump all the way from reciprocal lattice vector to 0. It can go to 0 smoothly. And so for this reason, we get this, instead of a sharp plateau transition, we get this extended wild semimetal phase where the Hall conductivity varies smoothly. Okay? But so this analogy, basically because this is just an extended phase that's analogous to the quantum Hall plateau transition, this suggests basically absence of localization for the same reason as it's absent at the 2D plateau transition. Okay, of course, this is not an unconditional absence of localization. I mean, if I add sufficient amount of disorder, I can always localize everything in any dimension. So just as in the 2D case, basically the statement is that there is no localization as long as disorder is not so strong that it destroys this 3D integer quantum Hall phase. So as long as there are 2 distinct insulators, one having this Hall conductivity and one having the Hall conductivity 0, the statement is that the intermediate phase is going to be a metal, a delocalized metal. Okay? Even the wild nodes generically are destroyed by disorder, as Shijun discussed yesterday. Okay? And I will show you some pictures that are similar to her talk. But the metallicity remains. Okay. Okay. So yeah.
So would that suggest that the magnetic wire of semimetal and non-magnetic wire of semimetal would be different in response to?
Well, no. So I think this actually generalizes to non-magnetic as well, as long as you preserve time reversal symmetry. Okay. Yeah. Okay, so let me give you two arguments for this absence of localization, one qualitative and one more mathematical. And let me start with qualitative in case I don't have time. Okay, so let's first think about a single wile node, right? So, well, in real wile semimetals, nodes always occur in pairs, but let's start with a single wile node. Now, so single wile fermion is anomalous in the sense that, again, it cannot exist in 3 dimensions. It can only exist on the surface of a 4-dimensional quantum hole insulator as its edge state, right? And so for this reason, basically, a single wile fermion can never be localized, okay? Well, another way you can see that is basically because backscattering is impossible in that case, because basically spin is locked to momentum, right, near a wile node in this way. A backscattering while preserving the spin direction is impossible. So for this reason, a single wile fermion can never be localized. So what this implies is that localization can only arise from internodal scattering, right? If I have a pair of nodes, localization can only happen from impurity scattering that takes me between the two nodes. Okay. So let me then describe this process in a kind of quasi-classical way, right? So what I'm going to do, I will start by ignoring all the Fourier components of my impurity potential except the Fourier component that connects the nodes. Okay, and I call this wave vector K here instead of Q because Q is going to be reserved for, again, for something else. Okay, I will only take the Fourier component of my impurity potential, and that's at this wave vector. Okay, and let me first take this potential to have non-zero average. Suppose it's not disordered; it has a non-zero average. Now, this kind of potential breaks translational symmetry and opens a gap. It mixes the nodes and opens a gap. And now what I want to do is kind of in a similar spirit to what I talked about in the previous, in the first half of this talk, I'm going to restore translational symmetry at long length scales by disordering the phase of this potential while keeping the magnitude. Okay? And so if I manage to do that, then at strong enough potential, I'm going to have a localized insulator. Okay, this will be basically an insulator with some disorder-induced states in the gap, which will be localized at strong enough disorder. Okay, so if this works, then I can construct at sufficiently strong disorder an Anderson insulator. Okay. However, this again turns out to be impossible for very similar reasons. So basically, as we discussed in my first talk, the elasticity in this crystal, right, couples to electromagnetism in this way, right? So basically, the gradient of that phase, of that potential, enters into my electromagnetic response in this way, and this is just a generalization of this EZ wedge A wedge dA action, except now I have resized the Brillouin zone, so the coefficient here has become an integer. And that's just the gradient of the phase, right? It's the same phase as that theta that I talked about in the previous lecture. But now it's just the phase of this charge density wave potential, okay? Now, and so what follows from this is the following, that the vortex lines in that phase, okay, are not simple. So they actually carry gapless modes, gapless chiral modes, and the way to see this is basically to observe that in the presence of a vortex line, so if I take my d theta to be equal to 2 pi, along 2 pi times a delta function along some direction, let's say x or y or z, it doesn't matter, then you can show that this action, this Lagrangian, is going to be not gauge invariant. Okay, so gauge invariance is going to fail on that vortex line. Okay, and one can see very easily that this non-gauge invariance may be canceled by a one-dimensional chiral metal. Okay, so this is basically the well-known story of Cullen-Harvey anomaly in flow, which was discussed, many years ago in a high-energy context, in the context of axions, basically axion strings. So again, in our case, what this means is that the vortices in that phase of this charge density wave potential are going to carry a chiral metal. Every vortex line is going to carry chiral metal, with chirality determined by the sign of the vorticity, plus or minus. Okay? Now, so if I want to restore translational symmetry, so if you think about this for a while, the restoration of translational symmetry basically requires that those vortex lines percolate from one side of the sample to the other, right? And that means that I cannot have localization because I will have these one-dimensional chiral metals that percolate from one side of the system to the other. Okay? And this argument is actually very similar to the argument that there is a very similar quasi-classical argument you can make for the lack of localization at the 2D plateau transition, basically where the percolating puddles, right? So this is similar. This is a similar argument here. Okay, so again, so this simple argument tells me that yeah.
So maybe you want to clarify. I thought that exterior derivative square is 0. Is that related to your anomaly story?
Yeah. So d2 theta means that. So normally, of course, d2 theta curl of the gradient of theta is 0, right? But it's not 0 if I have a vortex line. Okay. Okay. So this is a simple pictorial argument. I can also construct a more mathematical argument. Okay. So well, I don't know how much time I have, but yeah, I'll try to go through this quickly. So basically, so let's start by considering this Weil semimetal with a particular specific model for disorder. So I will take this Gaussian distributed short-range disorder. This is always the most convenient model for any calculations, but the conclusions don't really depend on that. Okay. And let me first ignore quantum interference phenomena, which actually can lead to localization. Let me talk about first quasi-classical transport. Okay. So basically, quasi-classical transport in any metal can be described by a combination of self-consistent Born approximation plus ladder summation of ladder diagrams for the polarization bubble for the density response function. Okay. Well, let me start with the self-consistent Born approximation. So this is the equation for the impurity self-energy. Okay. And so here I need to take a specific model for my Weil semimetal, and for this part, it's actually sufficient to take the simplest model, just a single Weil linearly dispersing Weil cone. Okay. So this is the equation for the impurity self-energy, and so this is something that Shijun talked about yesterday. So you can rewrite this equation as an equation for the scattering rate, which is the imaginary part of that self-energy. The real part of the self-energy, at least in this model, is actually a constant, so it only shifts the overall energy, and if we keep the filling the same, we basically have to discard it or absorb it into the chemical potential. Now, this is generally not true. For more complicated disorder, it will generically shift the Weil points, but this doesn't really matter. Okay. And so this is the equation for my scattering rate, well written here in terms of the mean free path, which is df times tau. And so what you observe here is that this basically has a solution only for finite disorder strength greater than some critical disorder strength. Okay, and so this is the phase diagram that Shijun showed yesterday. So basically, for weak disorder, disorder is completely irrelevant, and I have a clean wild semimetal. While for the disorder strength greater than this critical value, I have a diffusive metal. Now, the existence of this critical gamma has been actually challenged by people who say that the rare region effects actually always make it diffusive, but for me, this is irrelevant. Okay? So what I want to ask is, what happens in this diffusive metal as the disorder strength is increased further? So does it become localized, or does it remain a diffusive metal? Okay? And well, so the density response in this diffusive metal is the same as in any ordinary metal. The density response function looks like this, with this characteristic diffusion pole. And from this, you can calculate the diagonal conductivity using the charge conservation, right? And the DC conductivity by taking the appropriate limits of Q and omega going to 0. Now, another piece of the response here is, of course, the Hall effect, right? And so here I need to calculate the Hall conductivity. I need to take a more sophisticated model where I explicitly have two Weil points. And it's convenient to use this. You can describe this in the simplest way by taking this basically 2D Dirac fermion model with a KZ-dependent mass, right? And the mass goes to 0 at the locations of the two Weil points. Okay? So then an important difference from the longitudinal transport is that while sigma XX only comes from states at the Fermi energy, okay, sigma XY actually generically has two contributions: sigma XY1, which comes from states at the Fermi energy, and sigma XY2. Okay. This is actually related to the H state. So in a clean Weil semimetal, you only have sigma XY2. There is no sigma XY1. Okay. Now, in principle, it's possible that this disorder, strong disorder, which creates a finite density of states, may induce sigma XY1 at the Fermi energy. However, if you actually calculate it, you can easily see that it does not. So as long as 1 over tau is smaller than the bandwidth, okay, because the expression for sigma xy1 basically involves this integral of this 2D Dirac mass, which depends on kz, you can see that this cancels because m of kz depends on the change of sign and the location of the Weil point. So even in the strongly disordered Weil semimetal, sigma xy1 is still not 0, and sigma xy2, again, you can show actually has exactly the same value as in a clean Weil semimetal. It's not renormalized by disorder, and that's basically because it's given by the contribution of all the states below the Fermi energy. Okay. Okay, and so these results serve now as inputs for this nonlinear sigma model. So this is basically a description of quantum interference phenomena or interactions between these diffusion modes that may lead to localization. Okay, and well, so let me skip the details here. Basically, the important thing here is that this sigma model is going to have a topological term that looks like this. And this topological term precisely describes that sigma xy2, which is exactly the same as in a clean Weil semimetal. Okay, you can explicitly rewrite this as a purely surface term because this is a total derivative in the bulk, and this precisely describes my Fermi arc, which survives in the presence of strong disorder. Okay. And so then you can argue in a very similar way to the Bruskin's theory of the 2D plateau transition that this kind of topological term with a non-integer coefficient, so lambda here is non-integer, right? So it's any number basically in the interval from 0 to 1. This prevents localization. Okay, so well, you can show this formally mathematically by basically demonstrating that this kind of term leads to lack of gauge invariance if you assume localization. But let me just give you a very simple argument. The simple argument is that is in terms of the Fermi arcs, right? So basically, this topological term can be written as a purely surface term that describes my Fermi arc on the surface. Now, the fact that lambda is not an integer means that that Fermi arc, just as in the clean case, cannot span the whole brilliant zone of my wild semi-metal. So it has to merge with the bulk states. Now, the Fermi arc is chiral, so for this reason, it cannot be localized, right? But because it has to merge with the bulk states, this implies that there are always bulk states that originate from the Fermi arc that are also not localized, okay? And so as long as I have this chiral Fermi arc state that does not span the whole brilliant zone, I cannot have localization in the bulk, okay? Okay, so let me stop here. These are the conclusions, and yeah, please ask questions.
Questions?
I'm wondering if this self-consistent bond approximation impurity potential is coming in from the tau.
I mean, that approximation really doesn't matter. It's just it's just a way to obtain, again, the bare coupling constants for that sigma model, right? The most important result there is that sigma xy1 is not zero. It is zero. Sorry, I don't have to worry about that. So my sigma model just contains two couplings, sigma xx, which is something non-zero because it's a diffusive metal, right? And then sigma xy2, which is the same as in a clean wire semi-metal, right? So that's where that calculation enters. Other details are not important. I mean, you can do a more sophisticated calculation as long as it doesn't change anything qualitatively. It's going to be fine.
But so I think my question is, if this issue of absence of localization is a strong solver, is it true for some sort of magnetic disorder as well, or is it just
For magnetic disorder, you're saying? Yeah, I think this is a magnetic wire semi-metal to begin with, so I don't think magnetic disorder is going to do anything bad here.
More questions? Okay, I have a somewhat a broader question. So, are there numerical simulations that come out the physics you mentioned in the first part of the talk?
In the first part, in the fractional quantum Hall, no, I have not seen any. I mean, this would be, so we don't, of course, provide a microscopic model that would realize that state. This is just, that theory is just a, it's like a Chern-Simons theory of 2D fractional quantum Hall effect. This is just a description. It tells you what's possible, right? But it doesn't give you a microscopic model that would realize that. So, I mean, that would be, you would take some lattice model of a wire semi-metal and you need to add some interactions. Now, the simplest interaction that you can add, let's say just an on-site Hubbard U, right? This would likely, this can open a gap, but this will likely create that charge density wave. So you need to somehow frustrate the charge density wave. So add longer range interactions that would make the charge density wave frustrated and energetically bad, right? So that's a difficult problem.
Yeah. Thank you. Well, if there are no more questions, let